So we were bickering, and our boss said, you know, if you're going to bicker about what to do on your night off, we might as well send you to another and actually give you a night off. But you have to talk about it. So that's kind of our presentation. I'm Irene, and I do a lot of our in-house testing. It's my job to make sure that the math is right, and then I write all our technical files.
I'm Angie. I'm the in-house R expert at Hexadata. I work on the R interface between H2O and R, and I also work on some of the algorithms that PCA can use. We're actually part of the data science team. That's 75% women. And overall, our technical team has a 23% women, which is above average in Silicon Valley and makes Hexadata a pretty cool and diverse place to work.
We also brought Sergey, who is one of our clients and is putting H2O in production. And he's going to talk to you guys a little bit later about the production part of our kind of final.
But first of all, let me just tell you a little about what H2O is. H2O is an open source distributed analytics platform for doing machine learning on big data. So you can build the same statistical models that you're used to, such as GLM or GPM or in Forest. You can do it on much larger volumes of data that you probably wouldn't be able to import in, say, R. For example, on a distributed cluster, we've actually been able to run a logistic regression on an entire terabyte of data and have it finished in just a few minutes. So that's a huge leap forward and means that people who use our software can leverage all their data rather than having to worry about subsampling or how to massage data to get running in smaller, R or something. The other cool thing is that we have a very intuitive web GUI interface, which I'll show you soon. And it makes building a very complicated and sophisticated predictive model very simple. You can just click a couple of buttons and change your parameters and run it, and it'll get going. For those of you who are more comfortable with other languages, such as R and Scala, we should also hooks into those. So for example, in R, you just download our R package, and you can write R scripts, and it'll run in the background on H2O. So briefly, we're going to walk through a practical problem today, which is what movie should I re-nice you tonight on our rare night off from work. And this will give us a chance to show you the workflow in H2O, from importing the data set to building a model to doing a prediction, and finally using that prediction to figure out what movie we want to see. This can be easily extended to a production setting for customer use cases such as recommendation engines.
So we started with the open source movie lens data. And it's really super simple. It's like a few demographic variables, and then it's classification features on movies, and we just arbitrarily pulled the first 5 classes to show you guys that they're overlapping in the sense that they're not exclusive. And we pulled the 1 to 5 Likert ratings and just dumped them into a binomial variable for like or dislike. And we have already pulled stuff up in H2O mostly for simplicity. But this is what the data are going to look like. So you can see that we have some basic information, gender, occupation, and then probably we have our recorded variable. Yeah. All right. So we're going to run through a GPM model. So maybe we can find it. So I think that GPM is a really good kind of ensemble learning method. The GPM that we implemented is a fully sequencing decision tree model, and we really like that a lot because it's I don't have much trouble where it works well when you don't necessarily have a graphical model that you want to work with. So this is the GUI that we've been using, and it's something that our engineering team has worked really hard on to try and make what often appears to be very complicated data science more accessible to people. And while we're doing that, we'll build the GLM model so that you guys can kind of see the difference in the classification error rates on whole data sets, which is really where the rubber meets the road, I think. Okay. And try to talk into Joe.
So while GLM is running, we're going to try a second model, GLM, and we're going to use the same data set and same response, which is the like, 0, 1, in which case the family is a binomial, so we run a logistic regression. And we're going to ignore a couple of columns. These are just sort of IDs and things that were in the movie lens data, but which aren't really going to affect or make much difference in our model. Binomial, and we're going to do a ridge regression, so alpha 0.
A ridge regression is application of all else penalty.
And that'll help basically prevent overfitting and allow our model to be more generalizable when we do prediction. So GLM is pretty quick, as you'll see. This will finish in just a couple of seconds, and here it is. So GLM is nice because you have these coefficients, so you can see how the location or occupation affects the polynomial log odds of this movie being rated highly, basically. And if we go down a little, we can see the confusion matrix. So here you see that it's really cool. We can change the threshold for deciding whether 0, 1 on our binomial, and it'll change the ROC curve here and change the confusion matrix. You can use this to sort of tune your parameters very easily.
Are you running locally?
We're running it locally here with really small data because we've been running it on AWS as presentations before. But when we're in-house and working on our servers or working on AWS, we normally run anywhere up to a terabyte of data.
Yeah, like the airlines, like the entire airlines data set, we've done the regressions and doing that on 16 nodes.
So let's just switch over to actually predicting on a data set that we kind of prepared. We collected some basic information about stuff that's coming out.
We're showing the
So you guys get the same sort of curves and confusion matrices, and you can definitely see that there's like a huge difference in classification error on the holdout set, which is data that's not ever been seen by the model before. And just to give you guys a sense of scale, I think our holdout set was 75,000 observations, and then the model that we picked on was 100,000 observations. So it wasn't actually huge. We have 3 statistics and some major variable, which is a function of the number of splits that any variable contributed to, which is nice because it helps with interpretability, which is one of the problems with GPM, that it's not always intuitive for decision makers. So this means the age is a huge thing here.
Okay, so we'll go ahead and use GBM to do a prediction on some new movies that are coming out. The prediction process for GLM is exactly identical, so we're just showing GLM here. And the data is our movie prediction data.
And for the rest of us, Captain America, because she has
Oh, the way the data, I think that, okay, that's right.
No, that's user error.
So as you can see here, there's 3 columns. One of them is just 0, 1. 0 is you probably don't want to see the movie. 1 is you do, and that's just on a 0.5 threshold. But we're interested actually in the probabilities for the other 2 columns. And you can see with let's see, this one's a 0.7 and 0.3. So overall, we say, yeah, we probably want to skip that one. And we've summarized this in a little table here.
Mostly because the names are checking the prediction, and that's not very fun for anyone.
So GBM predicts that we will like 300, her and Need for Speed, but we should avoid Frozen and Peabody, whereas GLM predicts we should go with 300, her and but Captain America, and we should also avoid Frozen and Divergent. So I guess for computer programmers, we really like to see Spartans go around killing things. And fast cars, apparently. Cool.
So this is our very cute example, and we didn't address a serious question here, but this is very much the approach that we take when we go talk to clients and we help put models into production. And we do a lot of ensemble methods. We do a lot of daisy chain models together, and we really do go through a process of model predict, test on a holdout set, and then go back and try it again and again, and sometimes again. And to speak more to that is Sergey from Collective, who is working on putting this into production now. So, by the way, this is our motto. Andy and I, our boss, feels that it's appropriate, so I'll just share it with you guys.
Thank you. I'm Sergey Granik from the Science Collective. So we're a digital advertising company. You've seen two versions of this slide today, so I'll be quick with this. So there are publishers on the web, people who browse the web, and brands who want to reach their audiences on the web. When the browser opens the web page, the publisher provides the content. The publisher probably has an ad server that then calls the ad server of the brand. That used to be like that. Now there are companies like ours, like Collective, who are in the middle and provide the service between millions of websites, millions of properties, and thousands of brands. So we use cookies to track audiences, to track users online, and then we bridge between different devices to reach the right user at the right time. So I'm going to talk about audience modeling, and there are two flavors of that we're doing. One is called audience extension, which is where you have a given subset of audience, such as age, gender, income, interests, or viewing TV. So here, why do we even need to model? So there are companies out there that sell data that are third-party data providers that will tell you who and why you use name, email. The problem with that is that everybody can buy that data, first of all, and so everybody is going after the same people over and over again. Another thing is that for 20% of the users online, there are maybe 5 plus third-party data providers that have data on them. For another 40%, there is somewhere between 1 and 4. But there is 40% of cookies about whom no third-party data provider, and we work with about 30, have any data. And that's where we want to do modeling so that we can predict those 40% and reach untapped pools of users that will be valuable to that. Another example of that is TV viewing. So we work with companies like Brandtrack that have data from set-top boxes on TVs, on cable, and I think they're mostly satellite. What happens is when you tune in on a channel, the set-top box records what you're watching. So if an advertiser spends millions of dollars on TV ads, they would know that, okay, our TV ads are running in this period during this program. And then they could leverage their ads online, videos, and so they can come to us and we can find the people who are most likely to have watched that video on TV, we can find them online. Or we can find people who have not watched the program on TV. The way it's done is basically by using household information, in some cases one-to-one relationships. It's all anonymous, of course. But basically, we can bridge between TV audience to online. The problem is, again, that the pool of users who we can bridge is usually small. Maybe it's 1 million users. And campaigns that we're running run sometimes in tens of millions of impressions that we have to do. So that's, again, where modeling helps expand that audience and potentially. And so the second flavor is based on actions, and that's what Claudia was talking about before. So it's conversions of online purchases of rates. So how does it work? We build the audience cloud. We have a couple hundred million stable cookies, which means that we've seen them a few times. We have some data on them. We know where they browse. We know what type of browser they're using, and so on. We define the target audience. So this is the seed audience. It could be the third-party segment for which we have a license to use, or people who have converted previously or visited an advertiser website. And then we assemble, well, really millions of features, but we compress them to thousands. And on every cookie, we think about big predictive model with machine learning. We use GPU nets, and then we score every cookie in the audience. So we build thousands of models every week and score every cookie every day. So that's hundreds of billions predictions every day. Just that is sometimes challenging. And then we create targetable segments out of the users. So with top scoring users, we become a targetable set of users, and then we can modify the size of that, balancing the accuracy of prediction against the size of the audience. And then we build models daily or weekly and sometimes daily. We submitted a paper to KDD, hopefully it's going to get accepted, and you can find preprints at archive. So now I want to talk about where we are today and where we're going. So right now we are using R on Hadoop. We're really using Hadoop as a compute platform, so we're using streaming jobs to submit our hundreds of models at a time to our Hadoop cluster, and then get the results back. So the data size is a sample that we use to million rows by 1,000 columns, a few thousand columns. Where we want to go is to orders of magnitude bigger data samples, and so we're experimenting with H2O into production soon. We want to go from GeoNets nets to GBM. We just saw a perfect example where that would help with accuracy. And finally, exporting, currently we're doing in batch on Tisa, and with exchanges and users about whom we may not have enough information in the batch, and we want to go on the exchange and do predictions real time. To give you a scale of that, so we're processing probably over 100,000 requests per second at the time at peak. If you have even 100 campaigns, it's 10 million predictions per second. So this is it. Thank you.